Voltage difference. Justice, that's the fancy word for more batteries. Okay. Example 1. If we were to connect two 1.5 volt cells in series, what do you think the net voltage as recorded by the voltmeter would read? 1.5 volts, 3 volts, or 0 volts? And convince me. 3. Which makes sense. Oh, you know what? In my ski hill analogy, here's really what we're saying. You have one chairlift. It's a small chairlift. You get off, and you immediately get on another chairlift. And when you go up a 1.5 volt chairlift, get off and get on another 1.5 volt chairlift, then your total voltage is 3. What if I had one battery facing to my left, your right, and one battery facing to my right, your left? What would this be as a voltage? 0. We'll come to that, but you're right. What if, instead of having them in series, well, they're in parallel. Okay, let's talk about all that. So explain your answer using principles of physics. We just kind of did. You know what? Not even worth doing an explanation. It makes sense. It makes sense. In many portable appliances, CD players, flashlights are the classic one. You have multiple batteries in series because you need a higher voltage to get the bulb to glow nice and bright. Okay? The problem with doing this, though, is because because I total equals V total over R total. If you increase total voltage, if this number gets bigger, what happens to your total current? Gets bigger. And remember, current is the rate at which you're using up charges. If you put batteries in series, they'll burn out faster because you've increased the current. It's a trade-off. I'm sorry, there's no free energy. You can either get a brighter bulb, burn out faster, or you can get a dimmer bulb, but it won't burn out as fast. What would the effect be of connecting cells in parallel? What's the total voltage of this one, do you think? 1.5. And what we're saying here is, I guess skiers have a choice. You can go up this chairlift or you can go up that chairlift, but no matter what, the highest voltage you're getting is 1.5 volts. Now, why is that so nice? I total gets cut in half. These batteries would last twice as long. So I notice, for example, in my fancy schmancy graphing calculator, are these in series or in parallel? You know what? I bet you these are mixed because I notice they're alternating direction. I bet you these two are combined to give me 3 volts and these two are combined to give me 3 volts. But I have two 3-volt in parallel. These last a while. In fact, I have one calculator at home. I think it's going on 4 or 5 years. I don't use it very often. What I liked about these old TIs was when they started saying low battery, you still had about 6 months. They last quite a while. So you can either set them up in parallel, lower total voltage, but also then lower the current required. Or you can increase the voltage at the expense of bumping up the current. And this explains now an awful lot about how various, if you're ever putting batteries into an electric appliance, you can kind of ask, oh, these are in series, or these are in parallel. Now, just because they're side by side, by the way, doesn't necessarily guarantee that these are in parallel, because they could be, in fact, often if they're facing in opposite directions, they're wired in series, but they just couldn't fit room to have them like this. So as an example, any of you have those electric fly swatters at home, the bug fryers? Okay? Those, I bought one the other day. By the way, try touching it sometime. It hurts. You can just get an idea of why it kills the bugs. Okay? I think those, even though they're side by side, because the batteries are flipped in opposite directions, I think they're wired in series, just they happen to be parallel next to each other. Nerd trivia. Okay. What about rechargeable batteries? With a rechargeable battery, we recharge them by connecting them to a cell or a power source, or if you're plugging something in, but for now here, to a cell that forces current back through the cell. So here's our system. If we connect a 1.5 volt rechargeable battery to a 6 volt charger, what do you think the direction of the current would be in that ammeter? So here's my ammeter. Would the ammeter detect the current going to the left, or would the ammeter detect the current going to the right? Which way is downhill? How high? Pointing, don't write this down, this way. How high? Pointing this way. Which way is downhill? Yeah, the bigger battery. The bigger battery. So the current, what you're doing when you put a battery into a recharger is you're actually forcing the current, and here's where my ski hill analogy breaks down a bit. You're somehow running the chairlift in reverse. You're forcing current in the opposite direction. You're actually resetting the chemical reaction that was giving you this voltage and this current in the first place. Okay. Oh, and you always have some kind of a protective resistor. Otherwise, if you had no resistor there, this would be a short circuit. The current would be really, really high, which would cause everything to heat up. It might, in theory, recharge your battery really fast. No, it would do it so fast that it would damage things. In fact, you know what they often use for that little 10 ohm protective resistor? Have you noticed almost all battery chargers have a little light that goes on when it's set up right? That little light is your built-in protective resistor. It's quite clever. Why not use it to double up? Okay? So what would be the direction to the left? Or counterclockwise if we want to use some kind of circular direction? This way. What do you think the net voltage would be? If you go 6 volts up and you go 1.5 volts down, what's your net voltage? Yep. Now, my ski hill analogy breaks down a little bit. Well, I guess you can technically ride down a chairlift. That's really what we're doing, I guess. Okay. Does that explain your answer? I think we've just talked about it. So, in terms of the ski hill analogy, cells in series, like example 1, if this was 3 volts and this was 3 volts, then the total distance is 6 volts. It's like a 2 chairlift ride up to the top of the mountain. The disadvantage is this is more popular, more skiers, higher current. Cells in parallel, like example 2, are like 2 chairlifts which each lead to the top of the mountain. Opposite cells are like 1 up chairlift followed by 1 down chairlift. Okay? So now we're going to get pretty complicated. We will occasionally have to ski downhill through a battery instead of going uphill through the chairlift if we get nastier circuits. Principles to keep in mind. Positive means higher, negative means lower. Current flows downhill from positive to negative. So if you go from positive to negative, you're losing voltage. If for some reason you have to go uphill through a resistor, you're gaining voltage because you're going uphill. Will we ever have to do that? We'll have one really complicated circuit just to show you that we can, but it's harder than you're ever going to see on the test. Little comic there, but you can read it. Okay. So, example 4 says, find the voltage difference between points A and points D, and then graph them on the grid provided. Okay. I don't think we're going to graph it because I think the numbers don't work too well, but here's a circuit. What's the first thing that I would always look for? Remember? Total current. Did they tell me total current? Your hint is, first of all, what letter are you looking for in terms of units? Okay, so is there an amps somewhere? Yes. Is that the total amps? In other words, is that what you're getting coming off of the battery? Then they told me total current, this is going to fall apart. So did they tell me total current? Yep. So I'm not going to worry about rewriting this. I'm going to start to ski in Kirchhoff's laws, and if I know two, I know I'm going to start to do that right away. So how many amps right here, Rachel? How many amps right here? Which means it's the total current. How many amps right here? Yeah. Oh, how many volts? V equals I times R, 0.7 times 1. In your head, Rachel, what is 0.7 times 1? Which would leave 44.3 volts to deal with. Keep going. How many amps right here? Yep. I'm telling you, if you know total current, the question falls apart. It's got to be sequential. 0.7 amp. Oh, how many volts do we lose going through that one? Well, 4 times 7 is 28. 40 times 0.7. Is that also 28, I think? Yeah? Rach, how many volts high did we start? What did we lose here? What did we lose here? What must we lose there? Do the math either in your head or on a calc. It's going to be 45, take away 28, take away 0.7. 16.3 volts. Do I know anything else about that resistor? Oh, how many amps? 0.7. Oh, heck, I can find R, because R equals V over I. 16.3 divided by 0.7. I doubt this will work out nicely. Maybe, but I doubt it. How many ohms is that resistor? 23.3. Okay, I kind of found everything that I need. Anyways, this said, find the voltage difference between point A and point D. You know what? Since they said A first, really it should be the voltage difference like that. How many volts difference is there? You can get this without doing any math by reading. What was that? It's 16.3, right? Okay. Now, if you clipped up the voltmeter with the positive lead right here and the negative lead right there, you would read negative 16.3 and it's saying you've lost 16.3 volts. If you clipped up the voltmeter with the positive lead right there and the negative, wrong, in other words, it'd say 16.3 volts. But you know what? Most electricians, when you're in a rush, you almost don't care because you know you're losing voltage in a resistor no matter what. So you're actually ignoring the negative and the positive part. But you can certainly use that as a way to figure out which way the current is flowing. Oh, wait a minute, I thought I should have gotten a negative voltage because I thought I hooked this up right and I'm getting a positive voltage. I better be careful in this circuit. Something's wonky here. Okay. So what's the voltage difference between points A and 16.3 volt? Technically negative because it's a loss. Graph it? Well, yeah, it's kind of weird. Basically, well, I'm not going to graph it. That 0.7 gives me such a yucky scale, I'm not going to worry about it. What I want to get to is, we already answered example 5, didn't we? We filled in the resistor was 20, whatever it was, 23.3. I want to show you that we can handle something this ugly, example 6. Now this is much harder than you're going to have on your test. This would be, if those of you that take physics next year in university, certainly it would be fair game in the circuitry section next year. what do you notice? What's weird about this particular circuit? What? Someone said it. Yeah, what? Okay, more than one battery. Are they in the same direction or are they facing each other? I think they're, if I follow it, they're facing each other. So this is going to be tough. We can totally handle this though. So you ready? Which is the biggest battery? That's downhill. And this time we are going to label all of our arrows because this is uber complicated. So I am going to tell you right now, that's downhill. So certainly that way. Yes? Downhill? Yes? That way. Right? Now, I thought that was, oh, no, there's some current coming up this way. They got, okay. Well, that must still mean that's downhill. That's downhill. That's downhill. So certainly all around the outside, if I'm going clockwise, Vanessa, downhill. Okay. And I answered a couple of their questions. I got directions. Did they tell me total current anywhere? No. Did they tell me any current anywhere? Yeah? Okay, let's start there. By the way, this I don't want to try and rewrite in simplest form. This is going to be yucky to rewrite. So 0.5, okay. So Vanessa, how many amps right here? 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 No junctions. Okay, that's Kirchhoff's law. Ding, 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 ding. I know two things. Why don't I find the third? And I really am interested in the voltages here. So what's the voltage here? And that's a loss. Okay. Let's ski as best we can. First one I'm going to try skiing is the one that looks the least yucky. I'm going to try skiing this one. I think that's all downhill. Is it? Look at my arrows. Am I okay? All right. You ready? How high am I starting out? 4 volts. Let's remember that. Ski, 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 ski. What do I lose? I don't know. Ski, 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 ski. What do I lose here? And that's got to get me to the bottom of this lift. Well, the only way that can work is if I lose what over here? It's got to be. Otherwise, how the heck can I get a 4 there? Kirchhoff's law has to work for any closed loop. Do I know the current over there? No. Do I know the resistor? No. Okay. I'm going to ski another run. The run that looks the next easiest. By the way, the yuckiest run is this one because I got facing batteries. I'm going to save that for last only if necessary. The next nicest run, I think, is this bad boy. Okay. Started the battery. How high? Ski, 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 ski. What do I lose going through here? Don't know. Ski, 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 ski. What do I lose going through here? 2.5, leaving. 3.5, ski, 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 ski. Ah, what does this have to be? Has to be. Oh, do I know 2 things? I know 3 things. What's the current there? Really? You went 3.5 divided by 3.5 on your calculator, Grant? Are you kidding me? Are you kidding me? Are you kidding me? 3.5 divided by 3.5. It's 1 amp, champ. Man. Grant, how many amps right here? Okay, follow it. How many amps right here? Still. Right here, still. Now look, what's coming up from here? What's coming in here? What's got to be right here? Got to be 1.5. I'm telling you, we can handle this. Oh, so Grant, how many amps flowing through this resistor? Do I know two things now? Then carefully, can you find the resistance on your, you may use a calculator this time. Let's see. By the way, Grant, you times, a good habit until you get really good, I almost always just jot this next to the circuit, because if I just write that one out, I can rewrite the equation in my head properly every time. So R equals what over what? V over, once you write that, you'll just see it, and you won't accidentally trip on your brain. 2.5 divided by 1.5, oh, that's 25 over 15, 5 over 3, 1.66666, 1.67 ohms. Hey, are we, oh, missing one more thing. So, how many amps right here, Grant? Here? Here? How many go up? How many go this way? Keep going, keep going, keep going. That's the only missing blank. I think that's the only missing blank. Have we got everything now? Where I did it, sorry? Oh, well, I did it there on the resistor, but they specifically wanted to fill in that blank, so I'm going to make sure. Hey, if they have a blank or a question mark, I'm going to put an answer there. I'm a good test writer. Let's see. They wanted those. Did we get those and the direction? Yep. Now, you want to ski the ugly one? We can. Here it is. Okay? Ready, Ashley? How high? What do we lose here? Leaving 2.5. Ski, now we're going downhill. So we're going to lose 4 volts. 2.5 take away 4 is what? Negative 1.5. Now we're going up this resistor. So instead of losing 1.5, because it's technically negative, we're going uphill, which is gaining 1.5. When you go negative 1.5 and you gain 1.5, how high are you now? It works. That's complicated, but there is a nerdy thrill of pride in my heart that it works. So let me be clear, Jake, that is far tougher than I'm going to ask you in Physics 12, although it shouldn't be. Works. Practice, 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 and more practice. And then also today we're going to be going over the electrostatics test. I haven't done that yet. Let's see. Find the amount of power generated by a 40-watt bulb in series. Okay. By the way, I'm going to give you number one. I'm going to say this. I like number one. I like number one. I like number one. What I mean is, on your test, I'm going to give you a question where I don't give you a circuit. Here is your hint. Draw the circuit, and it'll fall apart. You try and do this in your head, ugly. How ugly? Grant sitting on his little chair, ugly. That ugly. Grant going 3.5 divided by 3.5, ugly. That ugly. 2 is good. 3 is far tougher than you're going to have on your test, but I always give it. See if you can get it. It's kind of nerdily cool. It's going to be literally a hopscotch to a hopscotch to a hopscotch to a, I think it's about 8 steps, but you can get there. I would start out by combining this as one single solitary resistor, and it does tell you that 2 amps flows through the 3 ohm resistor. Or sorry, combining these 3 as one, because they're in series. If you start going, it can get there. I'll almost certainly end up going over that one next class, but if you can get that, be proud. Number 4. Okay. Number 4 isn't asking you to analyze the entire circuit, just wants the net voltage. 5 is good. When it says explain your answer, You know what? My explanations usually just involve solving the circuit. So this has a switch. Emma, I would again do while it's open, while it's closed, do a before and after, and just solve it. And in this case, it wants you to find the voltage drop in the 5 ohm resistor. Okay. Number 6. What does it say about the bulbs in number 6? They are what? Did they tell you their resistance? Now, these can be done algebraically. I'll be honest, this is about where my level of algebraic breaks down. I would just make up nice resistors for those 3 bulbs. A nice one is usually, well, let's see, what would I go with here? Maybe make them each 2 ohms, or 4. 4 is a nice number to do math with as well. Make them all identical, and then solve it. Oh, and again, we're closing a switch. There's going to be while it's open, while it's closed. Except, what's this question asking you to talk about? Brightness. That's a synonym for what? Power. Okay. Oh, cool. This is also tougher than you'll see on the test. Did they tell you amps anywhere? So the strategy here is going to be rewrite this whole thing as one single solitary resistor. And it's got parallel and parallel and parallel and more. It's going to be multi-step. 8 is good. 9 is good. So far I've given everything, I know. 10 is cool. I like these. Also, by the way, I mean, look up for a second. How many amps? How many amps? I think they've given you total current. I think it's 6. It's going to fall apart, trust me. Here, did they give you 2 things? Did they give you 2 things? This is going to fall apart. I don't think you'll need to rewrite this whole sucker. That's always my last strategy. So 11. Mr. Dueck, why don't you just say all of them? Because I didn't know I was going to give you all of them, but I am.